Now we will discuss the third mode of convergence, that is converges in orth moment. Let r greater than 0, x1, x2 and so on, xn and so on be a sequence of random variables defined on omega f capital P. Such that the rth moment for the sequence of random variable is exist. The absolute sense expectation is going to be finite for n is equal to 1, 2 and so on. We say that this sequence of random variable converges to the random variable x in orth moment if the expectation of the random variable x, the orth moment, that is finite, and x also defined in the same probability space of course, and limit n tends to infinity, limit n tends to infinity, expectation of in absolute sense xn minus x to the power r, that expected quantity is going to be 0. We are keeping r greater than 0 and we have a sequence of random variable defined in the probability space such that rth moment exists for those sequence of random variable. We say that the sequence of random variable converges to x in rth moment provided the rth moment exists for the random variable x which is defined in the same probability space, and the limit n tends to infinity expectation the difference of this random variable, the rth moment, is going to be 0. If these conditions are satisfied, then we can conclude sequence of random variable converges to the random variable in the rth moment. We can go for the example to explain this mode of convergence also. That is let x1, x2, xn and so on be a sequence of random variables with mean mu, okay, it's identical mean, and variance of each random variable, that is sigma square, or exist. Both exist and is denoted by mu for the mean and the variance is sigma square. I am going to define the new random variable, that is sum of n random variables divided by n. Sum of random variable we usually use the notation Sn, but now I am going to divide that sum divided by n. So, I am going to use a notation called x bar. x bar is the random variable. It's a function of n. I'm not writing n in the left side. X bar is the sum of random variables divided by n. Fine. Or we can, another notation we can use as a function of Sn divided as a function of n, Sn divided by n. Either I can use a x bar or Sn divided by n, both are one and the same. That is sum of random variables. So this is the, so I am going to define this random variable for different n. We will go for finding first expectation of absolute of Sn by n minus mu the whole square. In absolute sense, we will find out what is the value of Sn by n minus mu square in absolute sense. That is same as expectation of, since it's a square, Sn minus n mu divided by Sn minus n mu whole square divided by n square. That is same as, I can take 1 by n square outside. If you see Sn minus n mu whole square expectation, if you find out the expectation of Sn, that is expectation of x1 plus x2 plus xn, all the expectation of xi's are same, that is mu, therefore it is n mu. So since expectation of Sn is n mu, so the expectation of Sn minus n mu whole square is nothing but variance of Sn. That is same as 1 divided by n square. I will make an additional condition. Xi's are a sequence of independent random variable with the mean is mu and the variance is sigma square. Therefore, the variance of Sn is nothing but variance of x1 plus x2 plus so on plus xn, and variance of xi's are sigma square, therefore it is going to be n sigma square. Therefore, this is going to be sigma square by n. We got the expectation of absolute of Sn by n minus mu whole square, that is going to be sigma square by n. Now let me apply limit n tends to infinity of expectation of absolute of Sn by n minus mu the whole square. Since n is in the denominator, this becomes 0. So this is the definition we wanted to convergence in rth moments. That means I can conclude Sn by n converges to mu in second order moment. The right hand side, it's not a random variable, it takes a value mu, that means it's a random variable, takes a value mu with the probability 1. So Xn converges to rth moment with the number r. In notation, we write Sn by n converges to mu in the second order moment. In the right hand side, mu means it's a random variable, takes a value mu with the probability 1. I have already written Xn by n as the x bar. So x bar converges to mu in second order moment. In statistics, we use the x bar, that is the sum of random variable divided by n, that is from the n random variable we call it as a sample mean. The sequence of random variable having the mean mu variance sigma square, so the mu is called a population mean. So the conclusion is if you have a population with the mean mu, and if you get a sample of size n, then the sample mean will converge to the population mean as n tends to infinity. That means if you, for a large sample, the sample mean will converge to the population mean, and this convergence takes place in the convergence in rth moment, where r is equal to 2 here, because we are finding the second order moment convergence is used. Therefore, sample mean converges to the population mean in second order moment. We move to the fourth mode of convergence, in almost surely. Let x1, x2, xn and so on be a sequence of random variables defined on the probability space omega f p. We say that the sequence converges in almost surely to the random variable x if the probability of limit n tends to infinity xn is equal to x, that is 1. So here the random variable x is defined in the same probability space. The probability of limit n tends to infinity xn is equal to x, that is going to be 1. Then one can conclude the sequence of random variable convergence to the random variable x in almost surely. So we write it xn converges to x, above the arrow you write a dot s. That means this convergence in almost surely. Suppose we make a event A is nothing but a collection of w's belonging to omega such that xn of w tends to x of w. In that case, when I say xn converges to x almost surely, if and only if the probability of the event A, that is going to be 1. If I make an event A, that is nothing but as n tends to infinity, xn of w will tends to x of w and collect those w's, that is going to be the event A. If the probability of that event A is going to be 1, then we can conclude xn converges to x almost surely. In other words, the negation of the event A, that probability is going to be 0. That means you collect all possible outcomes from omega which does not converge xn of w to the x of w, you collect those possible outcomes whose measure is 0, then we can conclude xn converges to x almost surely. That means it is the whole unit mass is attached with the collection of possible outcomes. Those outcomes are the outcomes of xn of w converges to x of w. Those outcomes satisfies xn of w converges to or tends to x of w as n tends to infinity. So, if you include those possible outcomes or w's, those possible outcomes whose probability mass is 1, or whichever is not satisfying this condition, those possible outcomes whose probability mass is 0, then you can conclude xn converges to x in almost surely. We will go for the example for this. Let omega f and p be a probability space. Let sequence of random variable defined on the probability space omega f p as xn of xn is mapping from omega to real line such that xn of w is equal to 1 plus 1 by n for n is equal to 1, 2 and so on. Now, we will go for computing limit n tends to infinity xn of w, where w is belonging to omega, limit n tends to infinity of xn of w, that is going to be 1. That means the set of all w's belonging to omega such that xn of w will tends to 1. You collect those possible outcomes, find out the probability of that. That is nothing but p of omega. That is same as 1. In that case, one can conclude xn converges to 1 almost sure. Because for all w belonging to omega, the limit n tends to infinity, xn of w is equal to 1. Therefore, finding the probability of w belonging to omega satisfying this condition, that is xn of w tends to 1 as n tends to infinity, that is going to be the all possible outcomes. That is nothing but the p of omega, that is equal to 1. Therefore, it satisfies the condition for almost surely. Therefore, xn converges to 1 almost surely. So, the same example can be considered for other mode of convergence also. That means one can prove limit n tends to infinity, the probability of absolute of xn minus 1 greater than epsilon, that also you can prove this is going to be 0. This implies xn converges to 1 in probability. Similarly, for the same example, one can prove the sequence of random variable CDFs as a limit n tends to infinity will converges to f of x, where f of x is takes a value 0 till 1, and 1 onwards it is going to be 1. Therefore, we can conclude the same example, xn converges to 1 in distribution. That means there are few sequence of random variable may converge to more than one mode of convergence. So that can be connected in one nice way. That is, suppose you have a sequence of random variable and the random variable x defined on the probability space omega e of p convergence in distribution, and we have a convergence in probability. Suppose some sequence of random variable convergence in probability, this implies convergence in distribution. The converse is not true. It may be true for some few problems. In general, it is not true. Therefore, I am not writing the upward arrow. Convergence is not true in general. Similarly, if you have a xn converges to x in the first order moment, this implies the convergence in probability. Converse is also not true in general here. Suppose you have a convergence in rth moment, that implies the r minus 1 and so on till the first order moment. But here again converse is not true because of two reasons. The first order moment exists, that does not mean that the second order moment is going to exist. Even if it exists, it does not imply the convergence takes place. Therefore, the converse is not true. Convergence in rth moment exists. Then you can go for till the first order moment convergence. That implies the convergence in probability, that implies convergence in distribution. Now I am giving the connection with the convergence in almost surely. That is xn converges to x almost surely. This implies convergence in probability. You see the different direction. Almost surely convergence implies convergence in probability. Convergence in probability implies convergence in distribution. Nowhere converse is true in general. There are some additional conditions you can mention for some sequence of random variable. Then we can conclude xn convergence in x in probability, that convergence in almost surely also. But for that you have to make some additional condition. In general, the converse is not true for all the cases. So with this relation, I am going to stop the convergence or modes of convergence. In the next class, we will discuss about the law of large numbers.